So hi everyone, and yeah, and this is Naveen. I will be the acting tutor for this optical microscopy and spectroscopy class, and so till now we have discussed the most of the important part of this lecture series, and we have to complete the last week 3 or 4 lecture videos, or that we will try to complete the 3 lecture videos by today, and I have the what do you call I have the questions for all this all these weeks. So we are going to put forth in the folder, and we are going to discuss in the next class. But before that, I will be giving an introduction about all of these questions. Okay, that's like an assignment. Okay, I want you to do this, and you would be getting a better idea how the questions will be asked from each of these things. Okay, you might be this new to this, but I think you can able this to access and deal with all of this. Okay, so the question is pretty simple. So first, essential quantum mechanics, you will be dealing with uncertainty principles, and let me share the screen for you guys. That would be uh, much better for you guys, I think. So yep, and first we will be dealing with the uncertainty principle. Okay, how all of these things been relatable to each other. So some of the mathematical symbol has been written over here, and you try to figure it out how the things can be written in a more convenient form for you guys. Okay, and probabilistic nature of in measurement, and Stern Gerald equivalent light photon at a picture PMT response, and linear vector space. In the week 2 we have discussed about the time dependent perturbation as well as the light matter interactions. What is the exact phenomena that will be happening when the light gets interacts with the matter? Okay, if there is, will there be any change? Will the matter get behave differently or not? And then each of this having a definite rules for that, and you are going to derive it out and give me a detailed explanation for this. And finally, third week we have discussed about the fluorescence and the spectroscopy, fluorescence intensity, whether it is decreasing or not, and then emission and absorption spectra, fluorescence lifetime also. And then fourth week we discussed about the second quantization as well as the Fock states, one of the most important point where we were able to determine certain parameter relatable to the light intensities, and then spontaneous and the stimulated emissions where the Jablonski diagram, okay, this spontaneous stimulated, okay, population inversions, okay, and the lasing in the media. Till now we haven't we have started the first lecture of this one, and we have to complete the 4 lecture parts, and today we will try to complete the first 3. Okay, so that we will get a better idea about it. So I will be uploading this in the lectures, the PPTs and everything, and you have to be in the position to sort this out, and have to submit it though. Okay, so let's start the session then, and let me go ahead with this one. So yeah, so first let's have a quick look at what we have been seeing. And in the last lecture what we saw that how do we analyze the population dynamics in a two level laser systems, in the hope of seeing if we can able to generate a optically pumped two level system or not. Okay, so I have mentioned that the analysis at the max. So what we see is that population can be equally distributed between the level 1 and the level 2 and not anymore. So that is the two level systems. It can the possibility of a population distribution between the levels 2 and 1. So often sometimes it might be a lesser also. So as a result you never exceed or never generate more number of molecule in the excited state. So why two level laser system is kind of a failure, because you won't be having a huge number of a population at the higher level or not in the excited state. So that if you do not regenerate, then it is not possible to have a laser system. So what they're trying to say is whatever that you generate, there should be a maximum amount of a population should be there on the excited state, and this process of having a more number of molecule in the excited state than the lower state for our emission, we call that a population inversion. Okay, so what is called that. So population inversion is nothing but the more number of molecules should be present on the excited level, and then all we tend to this is say that in the sea level system, but that is not possible because there has been a presence of equal number of population between the low and the higher level, but we need n2 should be greater than n1. Okay, and then we went on to discuss about the three level systems, and we are trying to pose one particular part. Okay, when we look at the energy level diagram, we have to understand what exactly the all of the things is all about. So let me give a glimpse about all of these things in the energy level diagram, because the next three classes we are going to focus on this and the next three lectures. Okay, to be very frank about. Okay, so yes, so let's draw the session then. Okay, yes, three level races. One, two, three. Is stimulated. Okay, it's happening from one state to another state. Yes, that is K and R. From here also it will get come to the ground star. Stimulated emission. Spontaneous emissions. True. Okay. So, and we have seen in the last class the total number. Okay, that is number of energy states n1 plus n2 plus n3. Okay, and then dn1 divided by dt is equal to kpst n3 plus kst21 n2. It depends upon the energy level. What are the parameters that's been in the conditions? We are going to talk about the ground form. So okay, so n3 n2 and again plus k sp 31 n3 and ksp 21 n2. Okay, so the same mirror goes for the uh, dn2 divided by dt also, and our final aim is to get a detailed view of dn2 minus n1 divided by this the total. Okay, that is a change in n divided by the n, and you can also mathematically express as 1 divided by. I will let you know this about what is the gamma functions and how they comes into the picture. K absorption divided by k sp p minus 1 and 1 plus 2 gamma k absorption divided by k sp plus 1. Okay, so the gamma function is normally the energy value. If it's less than something, whether the stimulated or spontaneous emission will be happening or not. So those values we will be dealing with it. Okay. KNR. So KNR. Okay. So in a two level system, what is happening? Okay. So the light interaction that we are actually trying to pump is exactly the same as that of the light radiation that is actually introducing the stimulated emission. So that is equal, N1 is equal to the N2, that is no higher in the things. So the same amount of intensity of a light that's been used, okay, to introduce the stimulated emission. As a result, it is constantly competing, the molecules is constantly competing to take the molecule from up to down or down to up, okay, the equal number, that's it. So they are, so as a result, what we have is that the higher population in the level 2 being not feasible, it's small in nature, okay. So it has to be greater in thing, then only the two level system will be working to the greatest point. In the three level system that we are trying to discuss, allows us to decouple the state. So what we are trying to pose, what is exactly the decoupling the state? Okay, we are actually stimulating. Okay, we are actually stimulating. Remember, K absorption that we have discussed in the previous classes is dependent on the incident light radiations. So the number of the molecule that are present on the ground state is dependent upon the absorption phenomenon. Okay, so is KST, KS also. Okay, so the K absorption and the KST. So this is on the pump laser, okay. So right, the laser that is taking, or the light that is actually taking the molecule from the ground state to the excited state. So the absorption, okay, the molecule that get absorbed, they will go from one state to the higher energy state. So that pump light, so to speak, what we are trying to pose it, so differentiate that from the laser emissions, how we can able to decouple it, we will call them as a KP. Okay, so right now we just want to have an expression, one phenomenon has to be in higher, then only population inversion can be achieved. Okay, so we are going to decouple the states. So so in order to differentiate then from the laser emission, we are going to call one of the form is a KP stimulated emission, that is this one, yeah, and arising from the incident pump light. Okay, so yeah, this is a KP absorption, KP this is stimulation. Okay, and this is of a higher energy or a higher intensity and high energy densities also. Okay, so the light in which is incident on this media can actually take the molecule to the excited state. So when the molecule gets the energy, they will go from one state to the higher energy state. But then the lasing per se, right, so that also requires, remember, okay, also require the stimulated emissions. Okay, they have to go from one energy level to the higher energy level. That is the whole idea of lasing. Okay, you have to absorb and you have to jump from one state to the another state also. Okay, so this is also the case with regard to the stimulated emissions. Okay, so there are spontaneous emissions, I am not actually showing you in the picture. Okay, but you can actually think of this. So think of it as them being here, okay, in the levels, in the energy levels. Okay, so okay, so what we can actually think of is, there are different kinds of spontaneous emissions. So one that is going like the orange. Okay, so the we are trying to explain the diagrammatic representation that we are going to make it. Okay, so and the happening. Okay, so some we will be just call it as a KSP, that is coming either from the second energy level either to the ground state. Some that's mean either coming either from the second to the first state in as a KST, that is a stimulated and the spontaneous. Okay, and there are two kinds of a spontaneous and the stimulated emissions, right? So here we are discussing about these ones. We want to differentiate these two. Okay, so we can differentiate in them by making it the state from where they are actually making the transition from second to the first. So here this spontaneous emission is happening from there to the state 1, and this spontaneous emissions okay, is happening there from the state 2 to 1. Okay, the state 2 to 1, the spontaneous emissions are there happening. Okay, so when we look at the literatures, they typically what they try to pose is numbers. Okay, they used to represent all of the state in terms of numbers. Okay, representing the levels to really capture where the transition is happening. So here we are going to denote them in terms of symbols as well as a certain energy levels, whether it is 3 to 1 or 3 to 2 something. Yeah. Okay, so the wiggly arrows that you are seeing right here, the wiggly arrows here, okay, represents the non-radiative decay from over level 3 to level 1. Okay, so this is a non-radiative state, that's why it's been named as a KNR32 as a superscript. Okay, so you can actually make the things write down the expression for the rate of this process also, how fast the things gets converted or how far the things gets moved on. And the first thing that comes to that we should keep in our mind is that total, that is nt is equal to n1 n2 n3, okay, addition for each of this rate process. dn1 divided by dt is going to be the influx. Okay, minus the I mean the outflux. Okay, influx minus the outflux, n2 minus n1. Okay, so we can write the kp stipulated. Okay, so, stimulated. Okay, kp, that is the, right now I'm trying to explain this formula. Kp stimulated, okay, n3, okay, so and plus kst, okay, stimulated, okay, with a subscript, okay, n2. Okay, so and and then when we go down to this to d2, and then of course the spontaneous rate comes out, constant comes into the picture. The spontaneous emission goes from n3, and spontaneous emission, that is n3 to 1, 2 to 1 of n2. Okay, so right now our ultimate aim is to create a n2 minus n1. Right now the dn1 divided by dt. Okay, so what are the things that comes in the picture with respect to the dn1? So kstp n3 and kst21. Okay, this is the 21. Okay, n2, again ksp, this again making and this impact from n3, and ksp21 n2. So the stimulated emissions has a role to play upon the stimulated as well as the spontaneous emission. The same goes for the n2. If we take the n2, the knr, the non-radiative decay, will be playing a major role in it. So finally we need to create a difference between them with regard to the total number and see what's exactly happening with it. Okay, so we can equally write down the rate equation for the dn2 also. Okay, and yeah, finally we should call them as n2 minus n1 divided by nt, that is the difference in n divided by n, the eigenstate. Okay, and that determines the number of atom that can actually potentially undergo this lacing action, that is a population conversion or inversion phenomenon. Okay, so if we go ahead and solve for it, we might be able to get the particular state also. And what we are going to do is the delta n, okay, which is n2 minus n1 divided by n. The logic is exactly the same. We can write down the expression for what in such a way, and now and yeah, d2 dn2 divided by dt, and at a steady state what exactly the dynamics is happening. And then we can expect there is a more number of terms that's been participating in the second level itself. Okay, and then yes, so and we also represented about this change in the state n divided by n, that is 1 minus gamma. Just give me a minute. So we are trying this to understand about what's exactly happening at the three level systems, and we are trying this to figure it out what are the ways that we can able to get the population inversion, why we can't able to get it from the two level systems. Okay, and there are certain other questions also there, and we are going to solve it out in the next couple of classes. Okay, I will be posting all the questions in the forum. Okay, Google, there is a forum, and there were nearly, there's a 20 to 25 questions out there, and 5 questions are from each of these units. Most of the questions are completely a mathematical one. I hope you guys will be able to solve it. And yeah, so right now we try to solve the population inversion problem with the 3 level systems, and then we will go to the 4 level systems also. Okay, 3 level system, and then we will discuss about the laser and then the 4 level systems. Okay, so why the 2 level laser system is being avoided and why people started to work with the 3 level system, that's the most important point that we are discussing about. Okay, this is one of the most important the diagrammatic representations that we need to get into the mind. Okay, we are trying to just sort out all of this problem with the help of this one alone. Okay, so right now the gamma function, why the gamma function plays a major role, and why it's been there, and what's exactly the role. Okay, so the gamma is essentially the ratio between the spontaneous between the level 2 and 1. Okay, and the knr is between this is the level 3 and 2. Okay, so the absorption and the spontaneous emissions. Okay, 1 minus gamma, 1 plus the 2 gamma. Okay, the denominator and the other, it's normally the ratio that is between the spontaneous as well as the knr. Okay, the spontaneous is normally happening between the second energy level to the first energy level, and the knr is the non-radioactive decay that's happening between the 3 and the 2. That is the most important function of the gamma. Okay, so whether the gamma function has to be greater than 1 or less than 1, if it's so greater or less than 1, what exactly the phenomenon that can occur. Okay, so to remain positive, one thing we want to make sure that the number k absorption by k spontaneous need to be greater than 1. Okay, so right now we are talking about the spontaneous. Okay, and the problem. Okay, so because the absorption here we are talking about the pumping rate also for the molecule to move from one state to the another state, that is the spontaneous emission rate also should be considered. And can this just a spontaneous emission rate. Okay, so this definitely we can actually increase the incident light intensity and make it 1 also. Okay, in the 2 level systems, whatever the thing that you are giving as an energy, it is getting equated between the n1 and the n2. So normally n2 should be greater than n1 for the population inversion to occur, but that's not occurring in the 2 level system. That's why people started to avoid that and people started working in the 3 level system. And the most common example for the 3 level system is the ruby lasers. Okay, so right now people try to work on with a much amount of energy intensity at the ground level itself, so that the molecule will be having the tendency to absorb this much amount of an energy to jump from one state to the another level. Okay, so this can just a spontaneous emissions also. And the important thing here is that we want to make sure that gamma is less than the 1. So if a gamma is 1, okay, or greater than the 1, then the whole process, okay, you are not going to this is separate a delta. Okay, so you should have to make a okay, play between the greater than or less than 1. Okay, so that the n2 minus n1 is occurring. Okay, so because what we know what is gamma itself, the gamma is the ratio between the spontaneous as well as the non-radiative decay. Okay, between the lasing levels, that is 2 and 1, and divided by the inflow rate, the rate of the constant k is the non-radiative rate. Because so it gets the molecules that are present in the ground level after absorbing this is the light, it jump from the ground state to the higher energy level, that is n3. Okay, and from the n3 to n2 it makes a non-radioactive decay, and then n2 to n1 it comes back in. Okay, so those are the important points that we have to discuss about. Okay, so for delta n to be in the above this equation, for delta n to be greater than 0, the delta n that we try to this mention here should be greater than 0, which would imply population inversion, right? So that's just the major phenomenon for it. N2 should be greater than N1 also, so which is essential for generating a net output or the stimulated emissions out of the lasers also. Okay, we need to get a stimulated emissions that should be greater than N1. And yeah, so for that to be happening, we see that the gamma needs to be less than the 1. So in order to make sure that your n2 is having a higher number of populations, and the gamma function should be less than the 1. Okay, and that is equal to the spontaneous emission happening between the level 2 and the 1. Okay, so uh, the non radioactive, there is a decay. Okay, constant need to be larger than. Okay, so that would make a particular, there is a sense for the population inversion to occur at a energy level. Okay, so we will be able to populate this level too faster than the spontaneous emissions also. So right now we are discussing about each of these levels, why the gamma function has to be less than the 1, why the non radioactive leakage risk have to be greater than 1, what exactly the reason is behind them. Okay, the spontaneous case spontaneous to 1 is basically the rate at which the molecule in the level 2 are the coming down. So the spontaneous from the level 2 is the coming down. Okay, so it's normally the let's put this diagram itself, it's proportional to the rate at which the molecules are coming down. So when we say that KNR needs to be larger than KSP, it means that we need to be able to get the inflow here needs to be larger than the KNP. Okay, so KNR should be greater than the KSP, mainly this is to get the inflow. Okay, so and the inflow can be larger by making the number of I mean incident. Okay, the power risk of incident can be the greater. It is, since it is a rate constant now, it is really there is some molecular properties also. Okay, so what we this are trying to possess is so yeah. So what we try to reserve process is the gamma, and the gamma should be less than the one that we know about that, and that needs to occur mainly for the pumping this action error to be done. Okay. Okay. So we know that the gamma is the ratio, the stimulated divided by the non-radiative decay, and yeah. So the KNR 32, that is 3 2. The molecule should come from the third energy level state to the first energy level state. KSP 21, and this is mainly to occur for the spontaneous reactions to take place. And another one point that we have to make sure that the K absorption is directly proportional to the number in terms of incidence. Okay. Okay, and we need to make a point regarding the efficacies. Okay, how the things will be there working fine. Okay, and, okay, sunlight velocity instead of say intensity. Okay, so the intensity of a light that's been striking at a particular interface for the molecule to jump from the ground energy level to the higher energy level, how the values are getting changed over a period of a time, how we can increase the efficiency, that also plays a major role. The efficiency, so is pump for 3 oil system. Okay, so yeah. So essentially what we are trying to tell here is that the net flow, okay, the amount of or intensity of a light that is striking at the molecule that are ground in the that are staying in the ground level have to be this larger than the net outflow. Okay, So the flow that is going this out. Okay, you can have the accumulations of the molecule here at a one particular point, but then the problem it is, we know that the spontaneous emission rate constant on the stimulated emission rate constants are related. Okay, both of the Kp and the Kst theories are completely related with respect to the energy levels. Okay, so then also we need to remember about the Einstein coefficients or even our second quantization right also. So both of them are related through the molecularly. They are related through R12, the matrix elements. So if you go through the last couple of classes, we might have just seen all of these things. I will write it down. So, for population inversion to occur, we know that it should be greater than 0. Okay, for population inversion. That is N2 greater than N1. Okay, we are running after this node only. Okay, and then R should be less than the 1, that is a gamma. The gamma, we know that it's a ratio. This is a non-radioactive decay. Okay, and another one also, KSP should be this one. Okay, and then normally if you consider about this graph, the K absorption is directly proportional to the K incidence or intensity. The intensity of a light plays a role in it. Okay, so this is how the things will be applying. Okay, so as I already mentioned in the line, so K stimulated T KNR32 is greater than or equal to KP31. So how they are coming reserve from the 3 to 1 or a 3 to 2 and a 2 to the reserve 1, as well as the stimulated emission has a role to play upon. So yeah, so any change in the incident mean that actually reduces, that is going to somehow affect the stimulated emissions rate also. So we have to be a little careful about the modifying certain things. Okay, but then when we are looking reservoir is to have the media where the KNR, the molecule for the transition either from 3 to 1 or 3 to 2 is really high. Okay, you can actually do that by cleverly changing the matrix in which these molecules are completely embedded in the solid state phenomena, the laser. Okay, or in a way we are talking about a solution that it actually by changing the solvent properties also, the solution as well as the solvent. Okay, you can actually play around with the KNR as well as and the other stuffs. KNR, the stimulation, the spontaneous. So, but the bottom line that we are trying to change and actually this put forth is, by choosing the media in a specific way, we can actually make sure that the delta n, okay, is greater than 1. So ultimately we need to achieve the population inversion, but the 3-level system laser and get a large amount of an energy. I told you that K absorption is directly proportional to the intensity. From that point itself, we can able to come to the conclusion that the 3-level system needs a lot amount of an energy for maintaining the population inversions. So that's why people started to work with the 4 levels also. Okay, and yeah, provided again there is this K absorption by KSP, where the K absorption need to be larger than the KSP. Okay, absorption should be larger than the SP. SP is the spontaneous emissions. So where we have to keep increasing the incident power, and we will try to see the things beyond certain incident power. We will start to populate the more number of molecules into than this one. So if you start to increase the powers, so the absorption value also increase, and the population will also be this increase at a certain level. So this is the key here. So the delta n also will be greater than 0, and not just any population n2, but the population here should be greater than the population at n1. So population inversion is being achieved only by increasing the amount of the power for the delta n2. Okay, if that conditions, we can say that it's not achieved straight away, because the population 2 is fed by the population 3, the non-radioactive decay that we have dealing with the beginning the one. Okay, and we need to take the molecule error from the ground also. Okay, so ground level or the level 1, so keep increasing the intensity, we will repopulate here and there, and some of the molecule will go down and stay there before it can come down by stimulated emission or spontaneous base also. Now if we do it for a sufficiently long enough period of keep doing it for a sufficiently long enough, the mean period or I mean this sufficiently high enough intensity, we can actually end up having the molecules at the level 2. So it's ultimately we will be increasing the population at the level 2 by providing a large amount of incidence energy. So the interesting phenomenon here is that one can actually populate this inversion, right? Plot this inversion, or to say that the ratio, that is delta n by n, or delta n itself as a function of the incident light radiations. Delta n divided by n, or delta n is the function of incident radiations itself. What you will see is that to start with all the molecules on the ground energy level, so we are plotting delta n, okay, as a function of incident light radiations. The plotting, okay, the plots, it's nothing but here, this is the incident light radiations itself. Okay, so let us see, we are plotting the delta n by n as a function of incident light radiation itself, and it starts with n2 minus n1 is basically the n1 is equal to n to start with a very low intensities first for the pumping reverse action to take place, very low and extremely low intensity. Okay, so 0 in the 0 in this axis, incident intensity. As you will see that here I am talking this about this plot right now. As you will see that the delta n will be minus 1, because basically delta n by n will be minus 1, because what you are starting with as is everything in the ground state only. So everyone in the ground resist state, we need a much more energy for this molecule to get energized and then pump up. Okay, so now the total amount is equal to n2 is equal to n1. Okay, as we keep increasing the incident intensity, at one point it crosses the 0, now it crosses the 0. Okay, and then approaches closely to the 1. It's never going to reach there, but approaches towards the 1. It's never going to, it's reach there, but it's trying to approach it, trying to make it saturate. Okay, it only K32 and K 32 by KST, that is nothing but the non-radioactive research decay, and then the molecule has a 3 pathways to follow, that is 1 3 3 2 2 2 1. Okay, that is a 3 pathway. Okay, so in another words, we would see that KSP, that is a stimulated, okay, the order would be somewhat like the either equal or greater than, okay, either it has to be equal or greater than 1. What we are trying to pose is, we just need to increase the intensity pretty high, so that considerable number of a molecule here, okay, in a particular period of a time, whatever the molecules that are present need to be lesser than this. Okay, one state to the another state, n2 should be this a greater less than the n1 for the population inversion to take place. This is what the population n2 need is to be greater than the n1. Okay, you will never be able to take, okay, every single molecule down to this level 2 also. So like there should be, this is some loss will also be there, and you won't be able to take every other molecule from one state to the another state. There will be loss percentage also will be there, and the energization, it won't approaches the, it won't reaches the 1, but it will try to just approach the n1. It tend to reach, but it never reach. Okay, it also depends upon the incident intensity only, that is a KAB. We know that KAB is a function of an incidence alone. Okay, so that's what we are actually, there's a plotting here, the plot, the graph that you are looking at it. Okay, and we would see that a large amount of light is used towards actually bringing the molecule, or bringing the number of molecule equal between the ground state as well as the excited state. So the efficiency of this process defined as the amount of the pump, the light intensity that you are actually putting in it for the amount of the emitter light intensity that you are going to get out. Okay, so efficiency you can think of end pump is the ratio between the other way around also, end lacing or laser by end pump also. Okay, so yeah, and give me a minute. And you need a much more amount of an energy to pump all of these things. Okay, so the first uh, and the efficiency, anyways we need to discuss about the efficiency, and we have already just plotted this one, n laser divided by the n pump. Okay, so because you are pumping much more amount of an energy and to raise the molecule to reach out to the population inversion, so the efficiency will be low, I believe so, but we are going to analyze it what exactly it is. So if we define the efficiency, we will see that the amount of a pump intensity that you require to get the laser output is very low. Even if you put a large amount of energy for getting the things to be done, but the output is very low for this three level or three level lasers. So there are these are there are laser practicals also. These are the laser with a three level system that can be approximated to three level systems also. In fact, we will see a little more in a detail in the further lectures. Okay, but before that we will take a look into the first laser to be discovered called the ruby laser, that's been made out of the ruby crystal. Okay, actually there is a three level system. Okay, so we are saying it actually very inefficient. Okay, it's not efficient, it's a very inefficient because you need a lot amount of an energy, lot of incident light. Okay, so for the conversion to take place. On the other hand, the question that we would like to ask is there a way to improve? Okay, so right now we need to use a large amount of energy for the molecule to go from one state to another. Is it possible for the molecule to reach a particular position with using a less amount of energy or not? Yes, clearly we have the chances, we have the leverage to improve also. The idea becomes very simple, and the moment when we tend to realize why we are having this kind of a trouble, because you are fighting against a number of a molecule in the ground state. Okay, so what we are going to do is we have created an extra state. If we were able to create an extra state, we can able to increase the number of population in one state with a less amount of energy also. Okay, so here we are discussing about the two level three level system. The two level system is just means that you can't able to achieve the population inversion. In the three level systems you can able to achieve the population inversion, but you need a large amount of a light to strike the molecules that are stayed in the ground state. So in order to overcome the problem here, you need to add an extra energy level. That is what do we have to create an extra energy state. So start accumulating so that your incident energy does not compete with the laser light itself, and this is being accomplished with the stimulated emission itself. So we can actually start accumulating the molecules in the excited state. So we try to accumulate, push all the molecule from the ground energy level to the higher energy level. However, what is happening is that you are actually the lesser emission, okay, is measured by the difference between the number of molecule between the two states, ground state as well as the lower energy state. Okay, so between which the lacing is happened. So the lacing is nothing but the population inverse. People used to put a different types of jargon words. The lacing is nothing but the population inverse, the energy level to energy needed to make a certain difference between the two states. So we are actually having a large number of molecule in the ground state, naturally, because it is being supplied by the stimulated emissions. Okay, the spontaneous emission is from here, and then the spontaneous emission is from as well as the stimulated emission. So if you take all of the specs, so you need to maintain a number of a molecule in the higher energy level, but the ground energy level is having a large number of molecule because you get a stimulated, the spontaneous, etc. Okay, so even from a 3 to 1 also occurs, 2 to 1 also will be there is occurring. Okay, so yeah, so the four level, how it will be looking like is, let me just draw the four level laser medium. So in order to overcome the problem, people started to work with the four level lasing sources also. absorption, K stimulation, Kn naught 3 2 2 3. I mean this is 4. You can say that 4. You can say this 2 2 1. Okay. So let me erase it. This is 4, this is 3, this is 2. This is KNR 4 3. Okay. KNR 2 1. This is 1. Okay, you normally used to represent the eigenstate as a Keck vectors. Okay. Okay. So we need to just maintain the difference between the states so that the reaction errors occurs. Okay. So if the natural extension to this would be, suppose if we had a laser system, the lasing occurs between the levels that is not inclusive of all the original ground state. Okay. So we could think of a laser system something like where the laser is happening. The happening is nothing but maintaining a difference between the two energy levels. So we can actually see practically maintain this level, the level is between the things. So there is no restriction is of having to have more molecules here, because they are, it is at the level, it is not the ground state, it is the higher than the is a ground state. Okay, that is the 2. Okay, it is being fed. The higher energy state is not the higher the excited state to which the incident light is being pumping. Okay, we are trying to accumulate a much more number of an molecule is at the higher energy levels. So as a result, what we are trying to segregating that competition, as well as we are going to segregating the levels to which it is actually lasing is happening. So in order to make a population inversion, we are making certain things. So we are actually there is no light that can be make, so that is there is no light that is matching this energy available in the systems. So non-radioactive decay or manner, so we are feeding on to the higher level of the lasing electronic states also. Okay, and as a result we will be having the lasing action between the 4 and 3, that is a non-radioactive one, and there are the stimulated emissions. Okay, and we have also have a non-radioactive, so that has been happening between the 2 and 1 also. Okay, so yeah, so we are actually after the expression n2 minus n1. Okay, to maintain a population there is inversions, that's what we are been trying to figure it out how we can achieve. So remember, for a 3 level state we started with 1 minus 1 and 0, and it was trying to reach 1 at some point, but it's not reaching. But what you will see is, because this level, okay, because this level, the level 2 is kept close to 0, because of, so that it demands the KNR to 1. So the 2 and the 1 will be remain close to, that is a non-radioactive 1. So what we will see is that in this level it can go from 0, and it can the delta, yeah, dn by this n, and can only be positive, it does not go negative at all. So it does not go negative, it's trying to maintain a positive impact, n2 minus n1, or the higher energy state minus the lower energy state, for the maximum number of molecule to stay at the particular energy level. So yeah, so and we can able to research generate, we can able to pump it through some other means also, and we are going research to see how, what are the ways that we can able to pump a large amount of an incidency, so that we can create a stipulated amount of a population in 1 hour energy level. But if we are trying to use a light to generate a light of a particular kind, then we need to pass this kind of a checks, quality checks. So in the coming in the lectures, we will see the property of the light radiation itself, and then we will try to talk about an important categories of lasers. Okay, so we know about the ruby laser, we will be talking about the ruby laser. We know why it is a failure, because it needs a large amount of an energy for the population to occurs at a one state. Okay, and we will be talking about the 4 level systems. helium neon lasers. And then a light intensity as a function of a time also, the light, the behavior as a function of a time, and compare it with other light the sources. Mercury lamp is there, helium neon lamp is also there. What is a special category and why it is useful in our set of an experiments, that equipment we use it for the scientific study. So yeah so if you have any doubts with this part, you can unmute the mic and let us ask them if you have. So okay, so yeah, just give me a minute. Say so the next that we are going to discuss, yeah, how. So in the previous part we have discussed about the population inversion to exist. Okay, so what are the conditions that we need to set a net emission of a light through a stimulated, okay, stimulated emissions, net coming out from the device through stimulated emissions, we need a population inversion. So why two level system and three level systems are complete failure when a two level system is being overcome by the three level system, and the three level system needs a large amount of power for the population thing reset to be maintained. Okay, so yeah, so for we looked at different possibilities of the electronic state configuration in the lasing media itself, and we are trying research to do our best in order to observe what exactly happening in each of the energy states. Okay, the different consistence conditions for the existence of a population in the motion. Okay, and then at the end we are finally looking at the four level systems also. Okay, this is the part, this is the four level system that you are seeing right now. Okay, let me see whether I'm presenting it or not. Okay, yes, I'm presenting. Okay, so we describe the four level systems as level 1, 2 and 3 in increasing order of energy. The process we indicate through the arrows, okay, for the things to go up and down. Okay, and we can actually go ahead and work out the expression for delta n by n, the population fraction of the population existing as a higher population. So it's nothing but we are trying to maintain a higher population at each of the energy states. The number of a molecule in the n3 minus the number of a molecule in the n2. So this is the most important part, 3 minus 2. Okay, so the lasing is happening between the levels 3 and 4. Okay, and this is where the stimulated emissions we are trying to get the stimulated iris only. Okay, in the non-radiated area where the stimulated emission is also a part of it. Okay, we call them as a lasing for the population inversion to take place. So we want to amplify at a higher rate also. Okay, and we can actually what we trying to propose is we can write down the expression for delta n divided by n. So what we are going to do is we are going to make it as expression errors analysis with respect to these four level systems, that is yeah, delta n divided by n minus k n r K21 minus this is the 21 and the KSP 32 dot N incidence divided by K absorption 2 3 and K21 plus K43, okay, plus KSP 32 dot K21 plus K21 dot K43. So this is a non-radioactive okay. So the difference has to be achieved from the N3 minus N2 and it has to be greater than 0. Okay, it should not be less than, then only the population inversion can be maintained. Okay, we should be remembering about the diagram also. So the superscripts, the subscripts represent the kind of transition that's been happening between the energy levels, okay, and where the transition is happening, and the non-radiative is a rate constant for the non-radiative the process happening, okay, the transition from the state 2 and the state 1, okay. The rate constant of what we exactly trying to deal with it is K21 divided by KNR, okay. So let's look at this particular energy level diagram, okay, what it exactly mean and what we are trying to talk about or understand it is about this particular transitions, okay. And this is a leap rate at which from the ground level, okay, is being depleted to the ground level of the molecule itself, okay. So it's coming here from 2 to 1, right, and 3 to 2 is also should be taken into the considerations, and that result in the spontaneous rate decay, and should be having a faster rate decay when compared to the K21 to maintain the higher amount of the population between two of the energy levels, K3 I mean 3 and the 2, okay. So and the delta that is has to be N3 minus N2, okay, the number of molecule in the third level minus the second level. So if we have the K and R be larger than 1 or I, mean that we want to have this greater than 0 as much as possible at all times, okay, for making sure that energy transition is taking place or not. We need to consider the positive fractions also, and yeah. We are saying as long as this rate is faster, we will see a residual errors amount here, which means it will be the best is 0 or more. So the depletion rate is larger than the supply rate, okay, both of the things that has to be known. So it is that the rate determining steps should also be considered, okay, which one will be the strong, okay. We will end up having there is some molecules or no molecules at all, some might be present at one level and the no molecule at all. It is never the case where you have more molecules here, unlike rest out or 3 level lasers where there is more number of molecule that at the ground state, because they were these two states were overlapping, most of the states were overlapping. So now as long as this is ensured in our molecule, we will always have this delta np is 0 or greater than 1 also, that is I must be there is a greater than 0, okay. We are try to plot this as a fraction delta dn divided by n. It starts with a 0 and goes up to the maximum. It can go up to there is about 1, and we will be that will be close to 1 only, that won't be reaching the 1, okay. So it depends upon the amount of light intensity also, this increasing, this is going to increase the light. So basically a summations, okay, adding up, okay. So we are uh, the we try to make sure that the population 4 to 3 is quite larger, okay, and trying to figure it out the pumping at a speed that is larger compared to the K21 and as well as the K43, right. So K21 and which is a spontaneous emission rate, okay, and the spontaneous emission the clearance rate, actually if we are pumping right, that is larger than the denominator, whatever that we try to deal with in the ratios. Okay, in order to achieve the thing that is greater than 0, a combined process should be take place. So so to make sure that everything is under control, we can actually make sure that things are happen in a defined way, and that is ultimately the crux of this matter. Okay, so if you take a material, even it's a 4 level systems, and we can recall or devise out this a certain conditions. First, let's start. Right now, what I'm trying to post it is, so using the 4 level systems, you can able to achieve spontaneous emissions to the defined values, to the defined conditions also. Okay, and we will try to see the what exactly the things are happening. Okay, so at each of the energy level states, 1 to 4, 4 to 3, 3 to 2, and the 2 to 1, and either of the states should be just higher interval for the population inversion to take place, as well as the lasing, and the intensity should be low enough when compared to the 3 level systems for the population inversion to occur. Okay, this is the total crux of this matter. Right now we will deal with the whole complete experimental setups. Okay, so yeah, so for example, if we have a medium like this, and that has been around with a coil, okay, and you have a mirror. Okay, it's to and froth. Okay, this is the total length. It is a length. See, you can solve it as, okay, it can be reflecting in different ways also. It's okay, I will let you know the rest about the things. Okay, and we call this as M1 and this as M2, and the lasing action is also taking place, and we are worried about the PMT to amplify some things, and R is equal to Ni. Okay, and we should be knowing this about the intensity of the incident light, I naught E minus E lambda C is or L Z. Okay, that C is nothing but the difference between the ground and the higher energy levels. Okay, and that is the del n. Nk minus Ng should be greater than 0 also. Okay, or Ng minus Nk less than 0, and in this case there are some phenomenon to be taken place, and we have to make sure that I of c is lesser than I of 0. I will let you know about what each of this denomination or denotation mentions about. Okay, so we call it as m1 and it is m2. Okay, we need to have a mechanism to actually import energy into the systems for the reactions to take place. So here we are actually talking about the optical pumping that we are producing or putting the optical mirrors. So having a discharge tube, this is a whole discharge tube, this is like a flash lamp, okay, wound around this media. Okay, flash lamp that's been wound around this media. What is happening is that the light flash that is generated in the discharge tube is going to energize the media. The light flash that is going to discharge, okay, is going to energize the media, and then the media is going to fluorescence, the light, the thing that the substance that is present in the media is going to the fluorescence in the meantime also. Okay, so it is so this fluorescence we are tapping this onto also. Okay, that has to be this okay enough, and it is the fluorescence we are tapping onto, and some of these are going to make this as a round trip up and down. Okay, to energize some of the molecules and extract more and more molecules in the excited, bring down the more and more molecule from the excited state to the ground state also, and we have, we are talking about the situations where we have created higher number of molecules as well as the excited states. So the fluorescent photons, when they there is a comeback, okay, they actually there is are going to bring down there is a more molecule to the lowermost energy levels and generate photons of their own kind also. So what would be the exact result in the lasing? Okay, when they come down, they will be releasing some photons of some fluorescence of some wavelength. Okay, but lasing is nothing but the light amplification through the stimulated emission of radiations. They come from higher energy level to the ground energy level. While coming out though, they say emit some of the photons, okay, that they will get emitted. Okay, amplifying the number density of the stimulated emissions photons that are created through the stimulated emission. Stimulated emission is the one of the most process because of this discharge, the light, okay, the passing from one end to the other, making a round trip, high, going from the higher to the lower, they are emitting something. So now would it ensure that we have a lasing? The answer is no. So let us do a little analysis of what is exactly that is happening over here. Okay, just give me a minute. So yeah, so this is the gain media. Okay, so that is the media through which we are hoping to gain or convert the light energy that is of one kind. Okay, we are going to the convert one form of energy into the another form. It is a light energy that is existing as an incoherent light. Coherent means single pass. Okay, incoherent means they can they have multiple directions. Okay, so that is being used to generate the fluorescence also. Now we want to make sure that this energy is delivered through this flash lamp is efficiently or is converted into energy of stimulated emissions also. So the photons of stimulated emissions. So in order to do that, we will go ahead and write down the gain equations or the equation. So this is the gain equations that we are going to deal with it. Okay, or the equation that describes what happened to the photon densities when the photon passed through a set up something is like this. Okay, so now for a moment, if let us forget that the fact that we are actually trying to amplify the number density of the stimulated emission of the photons. Okay, so let's think about the light being incident on a medium, right? What's exactly, this is the medium and that's been this incident. The medium is going to interact with this light, and we known from our initial classes that when we have a medium of some length, then we know what to do or to describe the intensity of the light that is traversing across the media when the media is going to interact with the light. So the light will be passing across the different sets of a media, and the matter is here what is exactly happening when the light interacts with the matter. So this is given by the simple Beer-Lambert's law. So we are going to determine the Beer-Lambert's law is nothing but absorbance is equal to molar extinction coefficient, the concentration as well as the length, the path length. Okay, okay, we're going to write this in terms of an z-axis. So that is the one. So intensity as a function of a z, okay, is given by yeah, so I of z, I naught e power minus e of lambda c z. C is the concentration, or you can just say is that. Okay, so the intensity at the beginning of the medium is e, okay, to the power epsilon function of the frequency, or lambda, epsilon function of the frequency, this is the lambda. Okay, so in terms of lambda, the times the number density or the concentration, this is the lambda times the concentration or the number density that is present, the length of the interaction, the path length. So the frequency, concentration, the length. Okay, so yeah, so the concentration that we are talking about essentially is, normally we do not have to do this because we are going to now talk about two kind of interactions here. Okay, there are two kind of interaction that's been existing. Okay, so one is absorption, another one is the stimulated emission. You got to absorb the things, you have to make sure that they go from one end to the other end, and the other end will be this coming down. So in a regular absorption spectrometer, I will tell you there is we do not have a molecule in the excited states, what exactly it is. So we ignore the stimulated emission term. Okay, we are going to talk about a stimulated emission eventually, and we want to take two is to recast this concentration in terms of number densities of the molecule present in the ground state as well as in the excited state also. So if we go ahead and write it, it is actually, we can write this terms of C. see in terms of a concentration also, number density in the ground state minus the number density. So the number density in the ground state minus the number density that is present in the excited state, the K. So for a 4 level atoms, okay, we can actually replace the actual numbers, okay, that we might be using. Okay, we don't need to get confused with all of these jargons of words. So first, if you're talking about the energy level in the function of frequencies, concentration and the path length, the concentration ground level minus the higher energy level. Okay, so yeah, so Ng minus Nk. So normally Nk is a 0. Okay, we take this as C. Okay, Nk is a 0, we take this as C with regard to the ground energy level. Okay, so for greater than Nk. Okay, so yeah, and we should be able to achieve the population inversion. Okay, so we can say that light is being absorbed by the media through interactions. We have a mirror, we have the discharge tubes, we are considering about the z axis as a path length, the concentration, the frequencies and the incident light. Okay, so here we are trying to replicate the with respect to the Beer-Lambert's law, and Ng is far more than greater, that's why we were able to achieve the population inversion errors also. Okay, and more number of molecules at the higher energy state for the emission risk among the emission levels, and population in motion, essentially this means delta n is in our case in Nk minus Ng, and this is greater than 0 implies Ng minus Nk that is lesser than 0 also. So we try to achieve many things here, and I'm going to plot it, write it down all of these things in a defined way. Okay, the frequencies with respect to z axis also we are going to write it down in terms of incident light. So what we can say is I lambda minus z is equal to I lambda O E minus E of lambda, that is an energy, Ng minus Nk, that is a concentration, and then the path length. Okay, and I the lambda comma 0 E, we should be worrying about that, and then Nk minus Ng and then z. We know that Nk will obviously go to the 0th state, and I lambda comma L I lambda comma 0 E minus E lambda N. And then now we will be talking about the total energy level states also. That is, this is the length of the media right now. So on the z axis we have star, now it's a length of this media, L represents, and this is difference between the n. Instead of k we are talking about the t right now. Okay, and what is exactly the reflecting surface is doing at each reflecting surface. One minus r, that tends to lesser. Why is that so? Okay, what's exactly happening with it? And the gamma function of 1 minus r lambda, then the scattering also is there, and finally we can denote that E is a function of gamma. So why? So we are going to deal with more number of y's, the scatter, the lesser, and all of these things now. Okay, so Iz equals to I of 0 e power minus the epsilon function of the lambda. Okay, so clearly the intensity will also be the function of a lambda. So there are different lambdas that get absorbed. Okay, the intensities, okay, different types of intensity will get absorbed. Okay, and for a given lambda of a z that at 0, okay, whatever the intensity from that point onwards, we are actually the intensity actually there is a goes down. We are trying to figure it out what's exactly happening with it. Okay, so epsilon a function of a lambda also, that times Ng minus Nk, that times 1. Okay, so now for in during the population inversion we just saw this a negative there is a value. We can actually write down this as epsilon to the power e to the power epsilon of lambda times Nk. Okay, Nk minus Ng. Okay, so that is 1. So this is the point that I'm taking this one. Okay, so what we are trying to pose is the gain, the intensity, whether the gain intensity is gained or not. Because of this gain in intensity only we can able to achieve the populations. Okay, and the same word is being repeated throughout the course. Ultimately we need to measure the population intensities. Okay, yeah. So this is incredible increase in intensity, and it is precisely because of the certain value, and we can actually create a population inversion state also. Okay, the media that we are talking about becomes a gain media, because when we actually normally pass the light through a media, it is going to absorb, but here because of the population in motion, okay, we are actually gaining the intensity that is coming out from the other end also. We will be talking a lot about this, and we are going to just make the certain things as common as possible. Okay, so we could see that the intensity as a lambda of z. So the intensity that is let me mark all these things in a different colors. Okay, intensity as a lambda of a z. Okay, so intensity as a lambda of a z, okay, is actually supposed to be same. Okay, so now this times, see, okay, intensity of a lambda, okay, e to the power minus epsilon of lambda nk minus ng, okay, times z or l. Okay, this is nothing but our population and that we have talked about all of these things. Okay, so how much of the intensity gain we will have as a function of the length of the gain in the medium. Okay, we know that Beer-Lambert's law in our 8th class, A is equal to epsilon c length, and this is these are the three stuffs that we are going to deal with it here. Okay, we have to talk about the reflection coefficient also. What is the fraction of the light that is so defined as a number of photons that are get reflected by the total number. Okay, so the mean number of photon that is reflected by the number of photons that are get incident also. Okay, so we will see that number is the best to be 1, but it is never equal to this 1. Okay, it can't, it try to just achieve the 1, but it can't be this 1. That's the one that we are trying to pose. So at every such reflection there will be a loss also. Right now we are worried about the gain. We need to take into account the losses. So the first loss we are going to talk about is the loss due to the reflections. Okay, that's why I'm talking about the mirror surface, and at each reflecting the surface, what are the losses that we can able to note it down. So the loss due to the reflection is mainly given by each of this mirror, and yeah, reflecting surface we also have a loss of 1 minus r that we are dealing with it. And now we will try to look at the gain per round trip also. So we would imagine we would take a photon, okay, that originated from discharge tubes, the fluorescent photon. Okay, to start with, what we have is the media. We have to excite the media, okay, such that everybody has gone to the excited states. Okay, and we try to actually make a trip reserve from this media position from one to the other. Okay, one end to the other end, goes back also, and we are going to talk about one full round trip and what are the gain and what is exactly the loss that's been occurring. That is twice the length of the entire cavity. So this is a distance between the two mirror, that is the capital L. We are going to estimate how much of the losses we can actually reserve. That's the photon. So what is the fraction of loss that the photon will occur or encounter, okay, when it goes through this entire trip? So the idea here is, okay, the intensity, the incidence, the gain the photon will have when it passes through the media. Okay, what's exactly happening with it? So we also know the probability of loss as well as the fractional loss a bunch of a photon will encounter. The whole system will set to gain only if the mean, the whole system will set to operate in generate the output only if you have a gain higher than the loss. So we are going to equate that to arrive at the threshold at which we will be seeing the lasing actions, the amplification of the process. So we are writing down the expression mainly for the gain. Okay, we can actually calculate the loss per round trip also, the reflection, the losses for the round trip that's been happening from the two set of a mirror between the discharge tube and the lasing actions at the z axis, and that m2 followed by m1, that is the thing that we have given, and 1 minus r times the I, okay, means that we will have another reflection loss also. Okay, so it is the two surface in general. We could, what we could actually do is that we capture all of these losses and then equate it with a coefficient, let us say gamma, and yeah, basically encapsulate this is a function of I minus or epsilon lambda. Okay, this is the thing. Okay, the loss, we are going to track down the loss that's been occurring at the whole of these things. So this is mainly because of the absorption of the emitted light. Okay, and also the losses of this photon due to scattering phenomenon, that is when sigma scatter, that also we have denoted. So we can encapsulate into coefficient, and we can also call it as a gamma. This tells you per unit length and how much of the losses that are the photon will suffers. Okay, if you formulate in that way, that pretty similar to the Beer-Lambert's law also. Okay, we wrote for the gain, we can actually write this expression as I, the intensity before at the start, I mean intensity of the round trip would be equivalent. Okay, and that is I is equal to I naught e to the power minus epsilon. Just give me a minute.